Okay, so last week on Wednesday we started talking about probability for our last unit, probability and statistics. And before we start talking about more about events, we talked about what an event was last week. Before we start talking more about events, I just want to remind everybody to try to get test 3 turned in. Remember, it's take home. It's in My Open Math. It's at the very top when you log into My Open Math, and you look at the course page. It's at the very top. Okay, so let's talk about events. Now we said last time that an event is either one outcome or several outcomes. So, for example, if we're going to toss a die, if that's our experiment or our trial, then an event would be tossing a die and rolling a 6. That would be one outcome. Or tossing a die and rolling an even number. Rolling an even number as an event is several outcomes because we could have a 2, a 4, or a 6. So that's 3 outcomes in that one event. So if we know the probability that an event will happen, we can easily determine the probability of the event not happening, so the opposite of that. So if E is a certain event, we call E with a bar over the top the complement, and it represents the situation where E did not happen. For example, if we let E be the event of rolling a die and getting a 2, the complement, or E complement is what we usually say, is rolling a die and getting a 1, 3, 4, 5, or 6. Anything but a 2. So we'll notice that, and we can work through this, sort of use reasoning to work through and find the complement of an event. So if the probability, or find the complement of the probability of an event. So if the probability of tossing a die and rolling a 2 is 1 chance out of 6, or 1/6, then the probability of not getting a 2 will be 5/6, because there are 5 other numbers that I could land on besides 2. So there's a 5 out of 6 chance of not rolling a 2. So this is the event, this is the complement or the opposite of that event. If you'll notice, when we add the probability of an event to the probability of its complement, we get 1. And this should make sense because remember that if an event is certain, the probability is 1. So if you know something 100% is going to happen, the probability is 1. Well, if you roll a die, you will certainly get either a 2 or a 1, 3, 4, 5, or 6. So the probability of rolling the die and getting a number 1 through 6 is certain, so it should be 1. So the sum of the probability of an event and the probability of the complement of that event will always equal 1, because an event and its opposite, those are the two things that could happen in that experiment, and one or the other is going to happen. So the probability of one or the other happening has to be 1. So the sum of the probability of an event and the probability of its complement will always be 1. And this gives us a way to find the probability of the complement of an event occurring if the probability of the event occurring is known. So what I'm saying here is that if we know the chance of an event happening, we can easily find the chance that it will not happen. So we're going to take this equation, the probability of E plus the probability of the complement of E should equal 1. So with a little bit of subtraction, subtracting the probability that the event will occur, so minus P of E, we get the following formula. So to find the complement of an event, we can, or to find the probability of the complement of an event, we can take 1 and subtract the probability that event occurs. So, for example, if I pull a random card from a standard deck, what is the probability of the card not being a heart? Well, we can easily find this. We could actually easily find this one just by looking at not being a heart as our event, but we can also easily find this using the above formula. So let's first of all find the probability of getting a heart. So I know that there are 52 cards in the deck, and heart is one suit. So each suit has 13 cards, right? Ace through 10, and then Jack, King, Queen. So all of the heart cards, there'll be 13 heart cards, right? So 13 out of 52, the probability of getting a heart will be 13 out of 52. All right. We can change that to a decimal, and in fact, usually probabilities written as decimals are easier to deal with. So we can change that to a decimal just by dividing 13 by 52, which is what I'm doing right now, and that's 0.25, which that makes sense because that's a fourth of the cards in the deck, so 0.25. So the probability of getting a heart is 0.25 or 250. There's a 25% chance that you will pull a heart from the deck if you pull a card. So what is the complement of that event? Well, the complement of pulling a heart is not pulling a heart. So we want to find the probability of, I guess we can say, heart complement. So that's just going to be 1 minus 0.25. And that's 0.75, right? If you have $1, you have to give somebody 25 cents. You get to keep 75 cents. All right, there you go. And if you, we could rewrite the 13 over 52 or 0.25 as 1/4, and then 0.75 would be 3/4. All right, this sounds good. Let's look at another example. We're going to look at these two questions together here. It says a couple plans to have 3 children. What is the probability they will have 3 boys? Okay, let's talk about this. What could happen? How could, if a couple has 3 children, how could they have children? What is the sample space, I guess? What are all possible combinations they could have? So let's look at the sample space of this for a moment. We may not, in fact, use the complement until the second question, but let's look at the sample space. So they're going to have 3 children. They could have all girls, so we could have GGG. They could have 2 girls and 1 boy. They could have 1 girl and 2 boys. right? They could have a girl, then a boy, and then a girl, right? So they could have three girls in a row. They could have two girls and then a boy. They could have a girl and then two boys. They could have two girls, but then they could have the boy in between. So notice how this is different because the children are born in a different order than this one, right? So this is a different way that they can have children. So two girls, then a boy, or a girl, a boy, and then a girl. Okay? They could also have all boys. They could have a boy and then two girls. Or they could have two boys and a girl. Or they could have a boy, a girl, and a boy. Now, I think those are the only combinations they could have, right? Girl, 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 boy, 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 girl, girl, boy, 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 girl, girl, boy, 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 girl, girl, right? Girl, boy, girl, boy, girl, boy. 4, 5, 6, 7, 8. Okay, yeah. So that's the entire combination. So we want to know that's the entire sample space of combinations of children they could have. So we want to know what is the probability that they will have three boys, so all three boys. Well, there is one situation in the sample space where they're all three boys, and there are 8 total outcomes, so I would say this probability is 1 over 8, or 0.125. So there's a 12.5% that they will have all three boys. So what is the probability that they will have at least one girl? Well, if you think about what three boys means, and that should say boys, what is another way to say three boys? If they're going to have three children and they're all three boys, what are they not having? Well, they're not having a girl, right? So we could say that this is the same thing as the probability of no girls. So that's the probability of no girls. The probability of three boys and the probability of no girls is the same thing, 0.125. All right, so we want to find in our second question the probability that they will have at least one girl. So no girls and at least one girl, they're opposites, right? They're complements. Having no girls is the complement to having at least one girl. So the probability of at least one girl, so I might say at least I can find that by taking 1 and subtracting the probability of no girls. I know the probability of no girls is 0.125, so this is 1 minus 0.125. And that's going to give me 0.875. So there's an 87.5% chance that if a couple has 3 children, they will have at least one girl. Excuse me. All right, so that's looking at the complement. All right, so let's move on here. So it says next, two events can be independent or dependent. Independent or dependent, and independent events are not affected by other events. So, for example, if you flip a coin and then roll a die, flipping the coin has no effect on the roll of the die. So these events are independent. On the other hand, if you are pulling colored marbles from a bag, as you take each marble, there are less marbles in the bag. So those events are dependent. Because one event does affect the other, right? So if you have green and red marbles in a bag, what's the chance of pulling out a red marble? Well, if you pull out a red marble, the chance of pulling out a red marble again lessens because there are less red marbles in the bag. So those events are dependent. So just quickly, let's take a look at each of these situations and we'll decide whether the two events are independent or dependent. So what if a fair coin is tossed 2 times and event A is the first toss is a head and event B, the second toss is a head? Well, actually, when you toss a fair coin, no matter how many times you toss it, the next toss does not depend on the first toss. There's still a 50% chance of getting heads or tails the second time you toss it, the third time you toss it. So these events, actually, events A and B, are independent. So I'm just going to put an I there. They're independent. Well, what if I said, though, that event A is it will rain tomorrow in Lee County, and event B is it will rain tomorrow in Wolfe County? Well, Lee County and Wolfe County are in the same area. They're pretty, they're close to each other. So if it rains in one county, so I notice that it's raining in Lee County, then there's a pretty good chance that if it's raining in Lee County, it's raining in Wolfe as well, since they're in close proximity and they're in the same area of the country, same area of the state. So these events I would not say are independent. I'd say events are dependent. Just because the two counties are very close to each other, so what happens in one county weather-wise probably has an effect on what happens in another county. All right, events can also be mutually exclusive or not. And mutually exclusive events are events that cannot happen at the same time. For example, if you toss a coin, you cannot get heads and tails at the same time. So tossing a coin and getting heads is mutually exclusive to tossing a coin and getting tails. However, if I said if you draw a card from a standard deck, you can draw a king and a heart card at the same time, because it's my phone ringing, sorry. You can draw a king and a heart card at the same time because there is a card that is a king of hearts, right? So if I said the event A is drawing a king and event B is drawing a heart card, those are not mutually exclusive because there is at least one event or one result where you can do those two things at the same time by pulling the king of hearts card. So these events are not mutually exclusive. So let's look at a couple of events and determine whether they're mutually exclusive or not. Let's say the first event is I toss a die. Event A is getting an even number and event B is getting a multiple of 3. Are those events mutually exclusive? Well, getting an even number, if I toss a die and I get an even number, I'm going to either get a 1, not 1, that's not even, sorry. I'm going to get a 2, a 4, or a 6. And if I toss a die and get a multiple of 3, I'm going to get a 3 or a 6. Notice that in each of these cases you can get a 6. So you can get an even number and a multiple of 3 at the same time. So these are not mutually exclusive. So not ME, I'll say. If you are following, so let's look at number 2. If you are following the directions provided by your global positioning system, event A is you turn right, event B is you turn left. Well, can you turn right and left at the same time? No, you can't. If your car pulls up to a stop and you turn left, you can't turn left at the same time that you turn right. So these events are mutually exclusive, so yes. They are mutually exclusive. All right. So now what we want to do is we want to consider events that we're taking together. 2 events that we're looking at together, or 2 or more actually. So we have something called and usually when you use the word and in mathematics, that means that something has to be true, or so if I use the word and, if I say A and B, then what I mean is that both A and B are included, or both A and B are true. So and means that whatever situation I'm in, that situation has to work for both A and B, okay? So if 2 events are independent, so the events have to be independent, the probability of both A and B occurring at the same time is given by the formula A and B is equal to the probability of A times the probability of B. All right? So A and B both have to happen at the same time. So let's think about this. Now, suppose we flip a coin and toss a die. Now, those 2 things are independent because flipping a coin, as we said, has no influence on tossing the die. What is the probability of getting a head on the coin and rolling a 6 on the die? Well, in this situation, if we let A equal getting a head on the coin and B equal rolling a 6 on the die, we're actually looking for the probability of A and B. And we have a formula for that. And that's just the probability of A times the probability of B, as long as these are independent events, and they are. So the probability of A, the probability of getting a head on the coin, well, we already know from a previous lesson that the probability of tossing a coin and getting heads, or tossing a coin and getting tails, are 1/2, because there are 2 outcomes and we're looking at one of them. And then the probability of rolling a 6 on a die is 1/6, because there are 6 possible outcomes and we're looking at one of them. So 1/2 times 1/6 is really 1/12. So the probability of getting a head on a coin and rolling a 6 on the die is 1/12. So how do we know this formula works? Well, let's look at this in a different way. Let's look at for the probability of A and B using the sample space. So if I want to get heads on a coin and 6 on a die, the sample space for tossing a coin and rolling a die is that I can get heads and 1, 2, 3, 4, 5, and 6, or I can get tails and 1, 2, 3, 4, 5, and 6. So there are 12 possible outcomes, and I need heads on the coin and 6 on the die. there's only one situation where I heads and 6, so that's 1/12. So this works out. This formula actually works out if we look at the sample space. This is sort of just a quick way to do that, or a shorthand way to do that. Somebody noticed a pattern, and we now can use that formula. All right, let's look at another one. In a chest of drawers, you have socks and t-shirts. There are 10 pairs of socks in the sock drawer, and 6 of which are white. There are 7 t-shirts in the t-shirt drawer, 3 of which are white. So if you randomly pull out a pair of socks, then pull out a t-shirt, what is the probability? And let's look at these two probabilities. Okay? Now, are these two events independent? Randomly pull out a pair of socks, and then go to the t-shirt drawer and randomly pull out a t-shirt. Yeah, they're independent. There's not... Pulling out a pair of socks has no effect on pulling out a t-shirt. So they're independent. So we're looking for and we can use our formula. So we're really looking for, it says both pairs of socks and the t-shirt, both the pair of socks, and the t-shirt are white. So we're looking for white socks and a white t-shirt. So that means we just need to multiply the probability of getting white socks times the probability of getting a white t-shirt. So what's the probability of getting white socks? Well, how many socks are there total? There are 10 pairs, and 6 are white. Excuse me. So there's the probability of pulling out white socks is 6/10. And we can reduce that if we wanted to 3/5. And I think we should, just to make it a little bit easier. All right, what is the probability of pulling out a white t-shirt? Well, there are 7 t-shirts and 3 are white. So the probability of getting a white t-shirt is 3/7. We can't reduce that, so I'm just going to bring that down. So since these are independent events, all I have to do is multiply these together. So 3 times 3 is 9, and 5 times 7 is 35. So the probability of getting a white pair of socks and a white t-shirt is 9/35, and if you want to divide that, that becomes 0.257. All right, let's look at the next one. You pull out a non-white pair of socks and a white t-shirt. So what we're looking for here really is the probability of a not white sock and a white t-shirt. So here, the white t-shirt, I know that basically that's just going to be the probability of a white t-shirt. These are still independent events, so I can use my formula. But here, how do I find the probability of not a white sock? Well, not a white sock is the complement of pulling out white socks. So really, I already know the probability of pulling out white socks. So what I need to find is the probability of the complement of white socks. Okay? So the complement is always 1 minus the probability that the event will occur. So in this case, 1 minus 3/5. I'm going to multiply that by 3/7. Because pulling out a white t-shirt, the probability of that is still 3/7. Well, what is 1 minus 3/5? Well, since 5/5 is a whole, 1 minus 3/5 I think will probably be 2/5, right? So this is 2/5 times 3/7. So 2 times 3 is 6, and 5 times 7 is 35. So 6 out of 35. And if we wanted to divide that to find a decimal, it would be 0.171. Yeah. So a 17% chance that the socks will be non-white. All right, cool. So that looks pretty good. Let's look at quickly another example. It says a fair coin is tossed 4 times. Find the probability of getting 4 tails in a row. So really what this is this is the probability of getting tails and tails and tails and tails, right? So because flipping a coin 2 times, those 2 events are independent, all I have to do is multiply the probability of getting tails times itself 4 times. So what is the probability of getting heads or tails? 1/2. So that's the first toss. Then there's a half chance of getting tails in the second toss, and the third toss, and the fourth toss. So there's a 1/16 chance, or the probability is 1/16, that you will get a tails 4 times in a row. All right, let's look at one more example, and then we'll talk about or instead of and. It says in a certain retirement community, 30% of the residents like playing bingo. So if you chose 2 random people, what is the probability they will both like playing bingo? So this is the probability of likes bingo and likes bingo, right? Basically, if you like bingo, 30% of the residents do, so that's 30% or 0.30. The probability that you'll like bingo is 0.30. And then the probability that the next person will like bingo is 0.30. And when you multiply 0.30 by 0.30, you get 0.09. So that's the probability that both people will like bingo. All right. So what if we're talking about the probability of A or B? Now, or is different. With and, both A and B have to be involved, or A and B have to be true, or A and B fit the whatever the criteria that you're looking at is. But if you're talking about or, then what you mean is the probability that just A occurs, or just B occurs, or that A and B occur together. right? So OR is any combination of A and B occurring is included in OR, right? So the probability that A or B or both occurring is given by this formula. If the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And what you're doing there when you subtract the probability of A and B, you're actually subtracting duplicate situations out so that you don't count an event or an outcome twice. So you're subtracting those duplicate outcomes. So suppose we flipped a coin and rolled a die. We want to know the probability of getting a head on the coin or rolling a 6 on the die. Okay, so this is really the probability of A or B. So the probability of A or B, with A being getting a head on the coin and B rolling a 6 on the die, will be the probability of A plus the probability of B minus the probability of A and B. All right, so the probability of A is what? 1/2, right? Flipping a coin, there's a half chance you'll get an A, or I'm sorry, that you'll get heads, half chance you'll get tails. The probability of B, which is rolling a die, is 1/6. And then we found before that the probability of A and B together, remember, we found that earlier in an earlier example to be 1/12. So when I take 1/2 plus 1/6 and subtract 1/12, I get, in decimal form, 0.583. I also get 7/12. So 0.583 is approximately equal to 7/12. That makes sense because if I change all this to twelfths, I get 24/12 plus, no, I'm sorry, I don't get 24/12, I'm sorry. If I change all these to twelfths, I get 6/12 plus 2/12 minus 1/12. So 6, 7, 8. That's 8/12 minus 1/12, so that'll give me 7/12. All right. So 0.583. Well, again, how do I know that this is true? Well, let's look at this just with the sample space. A or B. So I want to get heads on the coin, or I want to get a 6 when I roll the die. So I notice that, so what I'm going to do is I'm going to choose for my event anything that has a heads in it or a 6 in it, right? So this has a head, so that gets included. That one, that one, that one, that one. That one has both a head and a 6, so that one is definitely included. And then no heads or 6, no heads or 6, no heads or 6. Then that one has a 6 in it. So I have 1, 2, 3, 4, 5, 6, 7 chances out of the 12 to get either a head or a 6. Now you'll notice that I needed to subtract. Up here you'll notice that if I add 1/2 plus 1/6, I get 8/12. So this subtracting of the A and B, probability of A and B, is getting rid of the fact that I counted this H6 once with the heads, and I counted H6 once with the 6s, right? So notice half heads, but then there are 2 chances to get something with 6s in it. but I'd already included this H6 in the first count. So that subtracting of A and B is getting rid of those duplicates, or getting rid of a time when I counted twice the same thing. So that's why we need that in the formula. So 7/12, so everything works out. So this must be a formula we can use. All right, let's look at another example. It says, suppose we draw one card from a standard deck. What is the probability of selecting a king or a queen card? So we want the probability of selecting a king or a queen card. So I know that to use OR, I need to find the probability of selecting a king. I need to add that to the probability of selecting a queen. And I need to subtract from that the probability of selecting a king and a queen at the same time. Okay, so we're drawing one card from a standard deck. What is the probability of selecting a king or a queen? Okay, so the probability of selecting a king, there are how many kings in the deck? 4 out of 52. How many queens are there in the deck? 4 out of 52. And let me ask you this. Could I, if I draw one card, draw a king or a queen at the same time? A king and queen at the same time, I mean. No, you can't. These are mutually exclusive. So basically, the probability of drawing a king and queen at the same time is 0. So it says in the above example, the probability of A and B is 0 since the events are mutually exclusive. So now if I said, suppose we draw 2 cards, what is the probability that the first one or the second one, right? The first one is a king or the second one is a queen, then that could happen, right? But if we draw one card, the probability that it's a king and a queen is 0. So if I have 4 over 52 plus 4 over 52, that becomes 8 over 52, and you can reduce that if you want. But I could also just say that that is the decimal 0.154. All right, let's look at, I guess, a couple more examples. So suppose we draw one card from a standard deck. What is the probability we select a red card or a king card? So I want to know the probability that I select a red card or king. And sorry about me writing with this mouse. Okay, so now this is going to be the probability of red plus the probability of king minus the probability of red and king. So let's think about this, okay? So what is the probability of getting a red card? Well, there are 2 suits that are red, 13 in each suit, so there are 26 red cards out of the 52 cards. How many king cards are there? We just now said that there were 4. So 26 over 52 plus 4 over 52. But we have to subtract cards that are both red and king, or the probability of getting a card that's both red and king, so that we remove that duplicate. So I know there are 52 cards. what is the probability that a card will be both red and king? Well, how many cards are both red and king? Well, I know that there are 2 red kings and 2 black kings. So there are only 2 cards that are both red and king. The king of hearts and the king of diamonds, right? I think it's diamonds, right? Yeah, spades and clubs are black. All right, so I need to say 26 over 52 plus 4 over 52 minus 2 over 52. So 26, 27, 28, 29, 30. So there's 30 over 52 minus 2 over 52. And that's going to leave me with 28 over 52. You can change that to a decimal if you want. Now, we could have, we sort of reasoned through this, red and king, but you could have found that as well by using the formula. All right, let's take a look at this last example. We've got about 6 minutes left. It says the table below shows a number of survey subjects who have received and not received a speeding ticket in the last year. I like to look at tables because sometimes or often probabilities will be set up in tables, and it's a good idea to be able to it's a good idea to know how to use a table to determine certain probabilities. Find the probability that a randomly chosen person has a red car and got a speeding ticket. So notice this is and here. So we need to find the probability that the person has a red car, so red car, and got a speeding ticket. Well, right now, notice, or right now, let's think about this. Are these events independent? Well, I don't think they are, in fact, because have you heard that there is research? Have you heard research that shows that if people have a red car, they're more likely to get pulled over because of all the association, like with red cars as like sports cars, and you know, people who have a red car like to be flashy. You know, that's what the study has found, that's the perception, and that usually they get pulled over for speeding more often than other cars. So these are not independent. So we don't need to use the formula, but even if we needed to use the formula, we couldn't, because these are not independent events. But we don't need to use the formula because we can easily see that the intersection of the column speeding ticket and red car is 15. So there are 15 people who have a red car and got a speeding ticket. So that is 15 out of the total number of people in the study, which is 665. So that's not so bad. All right, now part B says, let's say we want to know the probability that a person has a red car or got a speeding ticket. So now here, let's use the formula. So how many people, or what's the probability that somebody has a red car? Well, let's think about this. Out of the 665 people, you'll notice that 150 have a red car. We're going to add that to the probability that you got a speeding ticket. So out of the 665 people, 60 got a speeding ticket. And we have to subtract the probability of A and B, remember. So we already found that. How many people have a red car and got a speeding ticket? 15 out of 665. So when you add 150 plus 60 and subtract 15, you get 195 out of 665. And you could do, you could change that to a decimal if you wanted to. All right, so you should be able to look at that, the working with events, that homework on My Open Math. Also, you'll notice that we didn't have enough time today to talk about conditional probability, so there are a set of videos and an information sheet that goes along with conditional probability. In conditional probability, what you'll do is you'll look at, well, what is the probability that a person has a speeding ticket given the fact that they drive a red car? So those events are not independent. So with conditional probability, you look at dependent events. And so there are some examples in videos online, and there's an information sheet to help guide you as you watch the videos. So next time in class, we will start looking at statistics. So we're done with probability now. We'll start looking at statistics. Make sure you turn in the Chapter 3 test. Be looking for Chapter 4 test. That'll be online, and it'll be like Chapter 3. You'll just take it, although it's going to be online because your final will be online, and I want you to have some practice taking a test in My Open Math online as well. All right. Well, if you don't have any questions, I guess we'll call it a day. So just let me know if you have any questions. Email me or give me a call, and I will see you on Wednesday. All right. See you later.
All right.
Bye-bye.